Albert Einstein spent the last 30 years of his life chasing after a theory of everything, an equation, perhaps no more than 1 inch long, that would allow us to summarize all the great laws of the universe. In other words, to quote, read the mind of God. And he failed. He failed because, well, the universe is much more complex than Einstein thought.
How big is the universe? It's one of the fundamental questions of astronomy. Thanks to evolving technology, astronomers are able to look back in time to the moments just after the Big Bang. This might seem to imply that the entire universe lies within our view. But the true size of the universe depends on a number of things, including its shape and expansion. As a result, even with all we know, the vast abyss of the unobservable universe is larger than the cumulative suite of all we can see. But when James Webb's sharp eye peered into the deepest recesses of the universe, it stunned the whole world with a series of glorious deep space sights, unveiling somewhat how big the cosmic scale truly is.
Or it could really be perhaps infinite in all directions. We don't know for sure.
Join us as we dig deep into how James Webb just announced the true size of the universe, challenging modern theories. To begin with, we know 2 crucial facts. The first is that the universe began just shy of 14 billion years ago in a singular event called the Big Bang. The second is that ordinary visible light has a finite speed. It travels at the amazing rate of 300,000 kilometers per second, or fast enough to circle the Earth about 7 times in a single second. We call the distance light can travel in a year a light year, which is equal to about 10 trillion kilometers. Another important idea we need to understand is the difference between the visible universe versus the entire universe. The first is what we can see, and the other is everything. This isn't so hard to understand. Someone standing on the roof of the tallest building on the planet can see in every direction for about 100 kilometers. However, the surface of the Earth is much bigger than that, and the curvature of the planet makes it impossible to see everything. With the universe, the limiting factor is different. It's the speed of light. If our universe were static and unchanging, the farthest thing we could see would be 14 billion light-years away. That's because if an object that far away emitted light, the moment the universe began, that light would just now be arriving at Earth. Light emitted from an object located 15 billion light-years away wouldn't arrive here on Earth for another billion years, so we couldn't see it yet. In our hypothetical static universe, the visible universe would be a sphere, surrounding the Earth, with a radius of 14 billion light-years. The entire universe might be bigger than that, but we would have no way of knowing since light from more distant locations hasn't arrived yet. But the universe isn't static, and that complicates things. The universe began in the Big Bang, and that bang caused the universe to expand. As it travels, light has to fight against that expansion, which takes it longer to get to you. To understand this, suppose a child stands 10 meters away from you and rolls a ball toward you at 2 meters per second. It will take 5 seconds for the ball to get to you. Now, suppose we have the same situation, with you standing on firm ground, but the child on one of those moving walkways you find in airports. Suppose further that the walkway is moving away from you at 1 meter per second. Because of the motion of the walkway, the ball will not take 5 seconds to get to you. It will take 10. Alas, it gets more complicated. While the child was 10 meters away from you when they rolled the ball, because of the motion of the walkway, the child will be 20 meters away from you when the ball gets to you. The same thing has happened to the visible light from the Big Bang. That light traveled for 14 billion years to arrive at Earth now. And just like the child on the moving walkway, the current location of whatever emitted that earliest light isn't 14 billion light-years away. It's now 46 billion light-years away. We see the light from where it was emitted, not where the emission source is now. In this way, Astronomers can say with confidence that the visible universe, which is the sphere around the Earth out to the distance of the oldest thing we can see, is 92 billion light-years in diameter. How can we comprehend such large scales? Well, frankly, to many of us, it can feel overwhelming to go straight to such magnificently large scales that span tens of billions of light-years. Thus, to understand the scale of the universe, we just have to build up a little bit at a time. One of the most convenient ways to begin is to go from the scale of a human to the scale of planet Earth. Although Earth is pretty big compared to a human, building up a little at a time doesn't seem so bad. Human beings are capable of climbing mountains, and mountains can easily rise up several kilometers in elevation over sea level. If you rise up in a hot air balloon or an airplane, you can achieve heights of tens of kilometers. Aboard a spaceship, you can escape to above Earth's atmosphere, achieving altitudes of hundreds of kilometers, comparable to what one would see from the International Space Station. And as you move farther and farther from Earth, you get to see what it's truly all about. It's a spinning, nearly spherical ball about 13,000 kilometers in diameter. From only tens of kilometers up, you can start to see its curvature, and once you're a few thousand kilometers away, you can take the full planet in one hemisphere at a time. Earth is extremely large compared to the scale of a human, but humans have ventured far enough away from planet Earth to obtain precisely this view, feeling a phenomenon known as the overview effect, the reason William Shatner cried when he went to space back in 2021.
I'm so filled with emotion about what just happened.
The Earth, however, is on the small side compared to many of the other bodies in our solar system. Uranus and Neptune are each about 4 times the diameter of Earth, while Jupiter and Saturn are more like 10 to 11 times our planet's diameter. The Sun, the largest object in our solar system, is a staggering 1.4 million kilometers in diameter, some 109 times the diameter of Earth, and capable of fitting more than 1 million Earths inside of it. But the individual objects are easy to comprehend if you're already the size of the Earth. And from the perspective of the Earth, it makes sense not only to look at the objects themselves, but the scales at which these objects move around one another, on the scales of planetary orbits. The Earth is the one we're most familiar with a mean distance from the Sun of 150 million kilometers. But this distance, the Earth-Sun distance, is only a little more than 100 times the size of the Sun itself, which is only a little more than 100 times the size of the Earth itself. All of a sudden, by just going up a little bit, from on Earth to above Earth's atmosphere, and by looking at the other objects in our solar system, we've gone from the scale of a 1.5 to 2 meter human to a 150 billion meter orbit around our Sun. Of course, our Sun is just one of a great many stars in the Milky Way, so the next step up is from the scale of things in our solar system to the nearest stars. This is a huge jump, but one that we can comprehend if we now begin our starting point, where our last endpoint left off, at the scale of Earth's orbit. Other planets, of course, are farther away from the Sun than Earth is. Jupiter's orbit is about 5 times the diameter of Earth's. Saturn's is 10 times as large. Uranus's is 20 times as great. Neptune's is 30 times as great. The Kuiper belt extends out to about double the extent of Neptune's orbit, and while there are a smattering of other objects beyond that, you have to go out to around 1,000 times Earth's orbit before you reach the innermost portions of the Oort cloud. But the Oort cloud goes out for tens of thousands of times the Earth-Sun distance, perhaps out to even more than a full light year. And then, once you start reaching distances of a few light years, you finally reach it. The next nearest star to Earth, Proxima Centauri, located 4.2 light years away. Stars are separated by distances that are usually measured in light years, and they add up fast. There are hundreds of stars within 25 light years of us, and that number rises up to more than 10,000 stars if you draw a sphere just 100 light years around Earth. At this scale, you start to notice that there are directions in space, where there are more stars and other directions have fewer. You're starting to see the structure of the Milky Way. In the direction of the galactic center, as well as throughout the plane of the Milky Way and particularly along its spiral arms, stars are denser and more numerous. Away from them, less so. All told, a galaxy is a collection of an enormous number of stars, but not an incomprehensibly large one. The Milky Way is a little over 100,000 light-years in diameter, which is to say that if a 1.5 to 2 meter human being lives on a 13,000-kilometer wide Earth, then that's the same ratio as the distance to the inner Oort cloud to the size of the Milky Way. Humans to Earth is the same as the size of Earth to the distance to the inner Oort cloud is the same as the distance to the inner Oort cloud is to the size of the Milky Way. And things, believe it or not, get easier from there. Stars are tiny compared to the distances between them. If the sun were a grapefruit in Seattle, WA, then the next nearest star would be a grapefruit in New York. But galaxies are not tiny compared to the distances between them. If the Milky Way were a grapefruit in Seattle, Washington, then Andromeda, the local group's largest galaxy located 2.5 million light-years away, would be a grapefruit in the same room, only about 3 meters away. In fact, the Virgo supercluster, spanning perhaps 100 million light-years, contains thousands upon thousands of large galaxies, and that would be like having thousands of grapefruits, clustered and clumped together in groups over the span of about a single city block. In fact, the large-scale structure of the universe is kind of like that. There are hundreds of billions of grapefruits, and tens of trillions of, say, oranges, mandarins, and kumquats that are smaller versions of galaxies, distributed across just under 500 such city blocks in all directions in all 3 dimensions, with ours containing the Virgo cluster located at the center. If 100 million light-years is well within our local supercluster, then it's only some 460 times that distance to the edge of the observable universe. From the scale of a human to the scale of the observable universe seems incredibly daunting. Humans are a couple of meters in scale. The universe that we can see extends for some 46 billion light-years in all directions. That means the observable universe, in terms of diameter, is nearly a full 27 orders of magnitude, or a factor of 1 octillion larger than a human being. It's easy to see why that's so wildly incomprehensible. Thus, one of the more intuitive ways is instead of thinking in conventional distances, to think of distances from a logarithmic point of view. In fact, a logarithmic map of the universe can truly capture the grandeur of the universe on a variety of scales all at once. Another interesting way is watching the scale of the entire universe under James Webb's views. As told, James Webb is humanity's most powerful astronomical observatory, revealing details about objects near and far at unprecedented resolutions in near and mid-infrared light. The advanced tools of this space observatory lets us see further into space than ever before, unlocking new insights into how the universe works. The images can be so in-depth that the results have been described as a new age of astronomy. Only 1 month after the first images were released, the successor to the Hubble telescope revealed new insights on how stars form, galaxies merge, and the early period of the universe. The images are a sight to behold, showing the cosmos in awe-inspiring detail. The discoveries have grown significantly since then, giving scientists a vast treasure trove of data to sift through. For example, through a tiny spot in Webb's first stunning image, researchers made a discovery that could shake up our understanding of the early universe. Astronomers analyzing the dataset discovered what appears to be 6 ancient galaxies. If it's correct, these galaxies would have existed when the universe was around 3% of its current age, roughly 500 million to 700 million years after the Big Bang. But these galaxies are far larger and more developed than what would be expected in the early days of the universe. Joel Leja, assistant professor at Penn State who was involved in the study, said the idea that massive galaxy formation began so early in the history of the universe upends our understanding on the early universe. We've been informally calling these objects universe breakers, and they have been living up to their name so far. In another deep field image, the James Webb Space Telescope captured a distant region of space in unprecedented detail, exceeding scientists' expectations. This section of space is known as Pandora's cluster, with the image revealing 3 clusters of massive galaxies coming together to form a megacluster. The combined mass of the galaxy clusters creates a powerful gravitational lens, a natural magnification effect which allows scientists to see the other galaxies. Ivo Labbe, an astronomer with the Swinburne University of Technology in Melbourne, described the image of Pandora's cluster as a stronger, wider, deeper, better lens than we have ever seen before. My first reaction to the image was that it was so beautiful. It looked like a galaxy formation simulation, Labbe said. We had to remind ourselves that this was real data, and we are working in a new era of astronomy now. Looking at another stellar nursery, the James Webb Telescope was able to spot thousands of never-before-seen young stars in 30 Doradus, nicknamed the Tarantula Nebula due to the appearance of its dusty filaments in previous images. It is the biggest star-forming region in the local group, the galaxies nearest to our Milky Way, and has long been a favorite for astronomers studying star formation. Webb's images helped to shed light on the composition of the Tarantula Nebula and also revealed protostars, very young stars that are still gathering mass. In time, it is expected that protostars visible in the image will eventually emerge and help shape the nebula further. While the NASA observatory is known for gazing as far as we can possibly look in the universe, its powerful instruments have also been used for discoveries closer to home. That is incredibly impressive to see even a tiny part of the universe in such great detail. However, note that the glorious sights that James Webb keeps revealing are less than a millionth of the whole universe. On the other hand, as we have emphasized many times before, that is merely the visible universe. What about the entire universe? How can we know about parts that are so far away that we have not even seen them yet? That's where things get interesting. It may be surprising, but astronomers are not 100% sure they know the geometry of space. It could be flat or it could be curved. While space is 3-dimensional, we can use a 2-dimensional analogy to understand what that means. In 2 dimensions, flat means flat, like the surface of a table. However, a 2-dimensional surface could be curved like the surface of a globe, but it also could be curved like the surface of a saddle. If it's curved like the surface of a globe, that means if you had a super-fast spaceship and traveled long enough, you could end up back where you started, like a plane flying along the Earth's equator. Astronomers have studied the data and have determined that space is flat, or nearly so. However, this determination is a measurement, and measurements have uncertainty. It remains possible that the universe has a very tiny curvature, but if it is curved, then the equivalent of the universe's equator is at least 500 times bigger than the visible universe, or possibly bigger than that. So despite not knowing the size of the entire universe, astronomers know that it is at least 500 times larger than what we can see. That number represents the distance one would have to travel to return to your starting location. In the same way that the volume of a cube is the distance along the sides cubed, the volume of the entire universe is, at a minimum, 125 million times bigger than the visible universe. The bottom line is that the visible universe is incredibly large, and the entire universe is truly enormous. Indeed, the entire universe could be infinitely large. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.